Look up at the night sky. What do you see? Stars, planets, distant galaxies shimmering with light, all part of the universe we know and can observe. But what if I told you that everything you can see, everything we've ever detected with our most powerful telescopes and instruments, makes up just 5% of the cosmos? That's right, 95% of our universe is made of something we can't see, something we barely understand, yet it's out there, shaping everything from the motion of galaxies to the very fate of the cosmos itself. This isn't science fiction, this is the reality of modern astrophysics, and what lies in that vast unknown is more mysterious and thrilling than anything we could have imagined. We're talking about dark matter and dark energy, two of the greatest puzzles in the history of science. Dark matter, an invisible substance that doesn't emit or absorb light, yet exerts a gravitational pull strong enough to hold entire galaxies together. And dark energy, an even more enigmatic force that's causing the universe to expand at an accelerating rate, pushing galaxies apart in a cosmic tug of war we're only beginning to comprehend. For decades, scientists have been trying to uncover the secrets of these hidden giants, and what they're discovering is reshaping our understanding of reality itself. So join me on this journey into the deepest mysteries of the cosmos. We'll explore how dark matter and dark energy were discovered, what we know and don't know about them, and why unlocking these secrets could reveal not just the hidden architecture of the universe, but also our place within it. This is a story of curiosity, perseverance, and the human drive to explore the unknown. By the end of this video, you'll see the night sky and reality itself in a whole new light. To truly grasp the enormity of what we don't see, we first need to appreciate the beauty and complexity of what we can. This is the realm of baryonic matter. That term might sound intimidating, but it's just the scientific name for the ordinary stuff you and I are made of. It encompasses every single atom, every particle that interacts with light, making it visible, tangible, and familiar. It's the planets in our solar system, the fiery ball of our sun, and the vast, swirling clouds of gas and dust in distant nebulae. When we gaze up at the night sky, every pinprick of light, every fuzzy smudge of a galaxy is composed of this baryonic matter. Think of it as the universe's building blocks. Every star is a colossal fusion reactor, forging heavier elements in its core. When those stars eventually die, often in spectacular supernova explosions, they seed the cosmos with these elements. That stardust then coalesces into new stars, planets, and crucially, the ingredients for life. The iron in your blood, the calcium in your bones, the oxygen you breathe, all of it was cooked in the heart of a long-dead star. This cycle of stellar birth and death is the story of the baryonic universe, a grand and beautiful tapestry that we are an intrinsic part of. And yet, for all its grandeur, this entire cosmic spectacle is astonishingly rare. This visible universe, with its hundreds of billions of galaxies, each containing hundreds of billions of stars, represents a mere 5% of the total mass and energy content of the cosmos. It's like looking at the foam on the crest of a massive, invisible ocean. We've been studying that foam with incredible precision, from the detailed structure of Saturn's rings captured by probes to observing the violent jets erupting from supermassive black holes. Our tools are magnificent, but they are fundamentally limited because they are designed to see the light. They are blind to the overwhelming majority of the universe that doesn't play by the same rules. This profound realization that we are surrounded by a reality we cannot directly perceive is what makes the search for dark matter and dark energy the most compelling detective story in all of science. For all its wonder, the universe we see is a master of deception. Astronomers first began to suspect they were missing something monumental, not by looking for the invisible, but by carefully studying the motion of the visible. The story starts in the 1930s with a brilliant, meticulous Swiss-American astronomer named Fritz Zwicky. He was observing the Coma cluster, a vast collection of over 1,000 galaxies bound together by gravity, millions of light years across. By measuring the velocities of these galaxies as they orbited the cluster's center, Zwicky could calculate the total mass needed to keep them gravitationally tethered. What he found was shocking. The amount of mass required to explain the furious speeds of these galaxies was hundreds of times greater than the mass accounted for by all the visible stars and gas within the cluster. The galaxies were moving so fast that they should have simply flown apart, like a merry-go-round spinning so violently that its riders are flung into the air. But they weren't flying apart. Something unseen was holding them together. Zwicky, in his characteristically direct manner, dubbed this missing ingredient Dunkel Materie dark matter. For decades, Zwicky's findings were largely considered a curious anomaly, an unexplained feature of distant galaxy clusters. The case was reopened with force in the 1970s by astronomer Vera Rubin and her colleague Kent Ford. They turned their attention not to clusters but to individual spiral galaxies. Their painstaking work involved mapping the rotation curves of these galaxies, that is, charting how the orbital speed of stars changes as you move from the bright center out to the distant, dim edges. According to the well-established laws of gravity, stars on the outskirts of a galaxy, far from the central bulge of mass, should orbit much more slowly, just as Pluto, in our own solar system, moves far more sluggishly around the Sun than the inner planets do. But Rubin and Ford's data revealed something astonishing and universal. They found that stars at the very edge of these galaxies were orbiting just as fast as those near the center. The rotation curve didn't fall off, it remained flat. This meant the gravitational pull holding these outer stars in their breakneck orbits was far stronger than the visible mass could provide. It was as if each galaxy was embedded within a gigantic, massive, and completely invisible halo of something. This was the most compelling evidence yet that Zwicky was right. Dark matter wasn't just a quirky feature of clusters, it was a fundamental component of every galaxy, including our own Milky Way. The final, undeniable proof came from a phenomenon predicted by Einstein himself, gravitational lensing. His theory of general relativity tells us that mass warps the very fabric of spacetime. A massive object like a galaxy cluster acts like a cosmic lens, bending and distorting the light from even more distant objects behind it. By studying the degree of this distortion, astronomers can create a precise map of the total mass in the foreground cluster, both visible and invisible. Time and again, these observations reveal the same story. The gravitational lens is far more powerful than the cluster's visible matter can produce. The light is being bent by immense concentrations of mass that emit no light whatsoever. We can literally see the gravitational footprint of dark matter sculpting the light from the distant universe. These three lines of evidence, galaxy cluster dynamics, flat rotation curves, and gravitational lensing, form an airtight case. The universe has a cosmic accounting problem of epic proportions, and the missing mass isn't just a small oversight. It is the dominant form of matter in the cosmos, outweighing everything we can see by a factor of 5 to 1. So we've established this monumental cosmic accounting error. The evidence from galaxy clusters, from spinning galaxies, and from gravitational lensing all points to one inescapable conclusion. The universe is filled with a form of matter that is fundamentally different from anything we have ever known. This is dark matter. It's not merely dark because it doesn't emit light. It is utterly and completely invisible across the entire electromagnetic spectrum. It doesn't shine, it doesn't absorb light, it doesn't reflect it, and it doesn't scatter it. Our most powerful telescopes, from the Hubble to the James Webb, are blind to it. They are instruments designed to see the light of the stars, and dark matter simply does not play that game. This profound invisibility tells us something crucial about its fundamental nature. The ordinary matter we're made of protons, neutrons, and electrons is called baryonic matter. It interacts through all four fundamental forces: gravity, electromagnetism, and the strong and weak nuclear forces. It's the electromagnetic force that allows it to interact with light, bump into other particles, and form the complex structures of planets and people. Dark matter, by stunning contrast, appears to be non-baryonic. It is something entirely new, a relic from the universe's earliest moments that is not composed of the standard particles in our textbook models. We believe it interacts via gravity, which is how it sculpts the cosmos, and it might interact through the weak nuclear force. But beyond that, it seems to be a ghostly presence, passing through the ordinary world without a trace. To grasp how strange this is, consider a simple thought experiment. Right now, as you watch this, trillions of dark matter particles are likely streaming through your body and through the floor beneath you and through the entire Earth itself, as if we weren't even here. This is because they don't interact with the electromagnetic force that holds your atoms together. You are, for a dark matter particle, essentially intangible. It's a one-way relationship. Its gravity influences the motion of our galaxy, but we have almost no effect on it. This elusive quality is precisely what makes it so effective as the universe's invisible scaffolding. In the early cosmos, ordinary matter faced a problem. The intense pressure from radiation in the hot, dense infant universe prevented baryonic matter from clumping together effectively. It was like trying to build a sandcastle in a raging hurricane. But dark matter, immune to this radiation pressure because it doesn't interact electromagnetically, was able to collapse into vast, web-like structures under its own gravity first. It formed a cosmic skeleton, an unseen framework of filaments and halos. Then, and only then, did normal matter, the gas and dust, feel the gravitational pull of these dark matter structures and flow into them. This is how galaxies formed. They coalesced at the dense intersections of this dark cosmic web. The dark matter halo of a galaxy like our Milky Way is a gigantic, diffuse sphere that extends far beyond the visible disk of stars, and it is the gravitational glue that holds the entire galaxy together, preventing those swiftly orbiting stars from flying off into the void. Without this unseen anchor, our galaxy, and every galaxy we see, would have torn itself apart billions of years ago. Dark matter is not just a minor component, it is the hidden architect, the massive foundation upon which the visible universe is built. Given its ghostly nature, how do we even begin to study something that refuses to interact with light? We observe its shadow. We watch how its immense gravitational presence distorts the universe around it, leaving behind a series of clues that are as elegant as they are undeniable. The first major clue emerged not from cutting-edge technology, but from meticulous observation of the familiar. Astronomer Vera Rubin's work on galaxy rotation curves provided a clear and simple anomaly that shattered our understanding of the cosmos. Imagine our Milky Way as a vast spinning pinwheel of stars. According to Newton's and Kepler's laws, which work perfectly within our solar system, stars farther from the galactic center should move slower in their orbits. The gravitational pull from the central mass weakens with distance, so an outer star like our Sun would be expected to amble along compared to a star closer to the bright core. But Rubin's data told a completely different story. She found that stars orbiting at the very outskirts of spiral galaxies were moving at nearly the same high speed as those near the center. The rotation curve, instead of falling off dramatically, remained stubbornly flat. This was like discovering that all the planets in our solar system, from Mercury to Neptune, orbited the Sun at roughly the same velocity. The only possible explanation was that there had to be far more mass in the galaxy than we could account for with stars and gas, mass that was distributed in a massive, invisible spherical halo extending far beyond the visible edge of the galaxy. This halo's gravity was providing the extra pull needed to keep those outer stars whipping around at such incredible speeds. While Rubin's work provided compelling evidence on the scale of individual galaxies, the phenomenon of gravitational lensing offers proof on a truly cosmic scale, showcasing dark matter's power in a way we can literally see. Einstein's theory of general relativity tells us that mass warps the fabric of spacetime. A massive object, a star, a galaxy, or a cluster of galaxies acts like a lens, bending the path of light traveling from objects behind it. This means that when we look at a massive galaxy cluster, it can distort and magnify the images of far more distant galaxies, often stretching them into faint, beautiful arcs of light. By meticulously mapping this distortion, astronomers can calculate the total mass of the foreground cluster that is causing the lensing effect. Time and again, these precise measurements reveal a stunning discrepancy. The amount of mass required to create the observed warping of light is vastly greater than the mass of all the visible stars, gas, and dust in the cluster combined. We are directly observing the gravitational signature of an immense concentration of invisible matter. It's as if we're seeing the silhouette of a giant by watching how it bends the light around it. Some of the most dramatic evidence comes from observations of colliding galaxy clusters like the famous Bullet cluster. In these cosmic accidents, the visible gas clouds, which are made of ordinary baryonic matter, smash into each other, slow down, and become separated from the total mass of the clusters. The gravitational lensing maps show unequivocally that the majority of the mass, the dark matter, has sailed right through the collision, completely unaffected. This proves that dark matter not only exists, but that it truly is collisionless and fundamentally different from the normal matter we understand. These gravitational fingerprints, from the orderly spin of galaxies to the dramatic warping of light, form an irrefutable body of evidence. We may not see dark matter itself, but we see its handiwork everywhere, sculpting the universe on the grandest scales imaginable. However, the most visually stunning and arguably the most convincing proof of dark matter's existence came not from a single galaxy's motion, but from a colossal cosmic car crash happening millions of light-years away. This is the story of the Bullet cluster, a system of two galaxy clusters that have slammed into one another in one of the most energetic events ever observed in the universe. What makes this collision so extraordinary is that it provides us with a rare and clear laboratory to separate the behavior of ordinary matter from the dark stuff, revealing their fundamental differences in the most dramatic way possible. When two such immense structures collide, the various components that make them up behave in very different ways. The galaxies themselves, vast collections of stars, are mostly empty space. During a collision, they tend to pass right through one another with very few direct hits, like two swarms of bees merging. The hot gas that fills the space between the galaxies, which is the bulk of the normal baryonic matter in a cluster, behaves completely differently. This gas is a seething plasma, and when the clusters collide, this gas smashes together, creating immense friction and pressure. It heats up to incredible temperatures and slows down dramatically, much like two clouds of smoke colliding and becoming entangled. This is exactly what telescopes observing the Bullet cluster in X-ray light detected. They saw two huge bullet-shaped clouds of superheated gas that had clearly been caught in the cosmic equivalent of a traffic jam, lagging behind the collision. Now, here is where it gets brilliant. Using the phenomenon of gravitational lensing, astronomers were able to map the total mass distribution of the entire cluster system. This technique doesn't rely on light emitted by the matter. It reveals where the gravity is strongest by showing how the cluster's mass warps the light from more distant galaxies behind it. The resulting map showed two distinct peaks of immense mass. Crucially, these peaks of gravitational force were not aligned with the lagging clouds of hot gas. Instead, they were located precisely where the galaxies themselves were the components that had passed through the collision largely unaffected. This separation is the smoking gun. The visible X-ray emitting gas, which constitutes most of the normal matter, got stuck in the middle. but the majority of the mass, the stuff creating the powerful gravitational field, had sailed right through the collision completely unscathed, just like the galaxies did. This proves conclusively that the source of this gravity, the dark matter, does not interact with itself or with normal matter in any way other than through gravity. It is truly collisionless. It doesn't slow down, it doesn't heat up, and it doesn't emit any form of light. The bullet cluster experiment effectively allowed us to see the two components of the universe side by side: the messy, interacting normal matter and the ghostly, non-interacting dark matter, forever distinct in their nature. This single observation dealt a near-fatal blow to alternative theories that tried to explain the missing mass by modifying the laws of gravity, because no modification of gravity could explain why the gravitational centers would be completely divorced from the visible mass centers in such a spectacular fashion. It stands as one of the most elegant and powerful validations of the dark matter hypothesis in modern cosmology. Accepting that dark matter is real and fundamentally different from anything in the standard model of particle physics was the first step. The next, even more challenging step is to ask the most obvious question: what in the universe is it actually made of? For decades, physicists have been developing theoretical candidates, particles born from mathematical elegance and necessity, each with its own unique properties and a thrilling story of how it might be found. The hunt for these particles is a grand scientific enterprise, combining the immense scales of cosmology with the ultra-precise, minuscule world of particle detectors. One of the longest-standing and most popular candidates is known as a WIMP, which stands for Weakly Interacting Massive Particle. The name itself is a perfect description of its hypothesized attributes. It would be massive, meaning it would have a heft many times greater than a proton, and it would be weakly interacting, meaning it would only feebly engage with normal matter through the weak nuclear force and, of course, through gravity. The beauty of the WIMP hypothesis lies in what physicists call the WIMP miracle. Calculations show that if a stable particle with these properties were left over from the incredibly hot and dense Big Bang, the residual abundance of such particles today would naturally account for exactly the observed density of dark matter in the universe. It's a breathtaking coincidence that suggests the answer might be elegantly woven into the fabric of cosmic history. To find them, scientists have built exquisitely sensitive detectors deep underground in abandoned mines or tunnels, shielded from cosmic rays. These experiments, with names like LUX, Xenon, and Panda X, are essentially giant vats of ultra-pure liquid xenon, waiting for the once-in-a-lifetime event where a WIMP might bump into an atomic nucleus and create a tiny flash of light or a minute charge. After years of searching with ever more sensitive detectors, the WIMP have stubbornly refused to show up, leading many physicists to broaden the search. This has brought increased attention to a much lighter and more whimsical-sounding candidate, the axion. Originally proposed to solve a completely different fine-tuning problem in particle physics involving the symmetry of the strong nuclear force, axions could also neatly fill the role of dark matter. Imagine a particle that is billions of times lighter than an electron, a ghostly wisp of a thing that would behave less like a discrete particle and more like a pervasive, sloshing energy field filling all of space. Because of their quantum nature, axions would be coaxed into revealing themselves not by a collision, but by converting into a photon in the presence of an incredibly powerful magnetic field. Experiments like ADMCs are essentially giant, super-cooled radio receivers, tuning through frequencies and listening for the faint telltale signal of an axion making this conversion. It's a search for a whisper in a cosmic hurricane, a testament to human ingenuity. Beyond these two frontrunners lies a zoo of other exotic possibilities. Some theories propose sterile neutrinos, heavier, right-handed cousins of the standard neutrinos we know, that would interact only through gravity. Others suggest that dark matter isn't a particle at all, but a primordial black hole, a relic from the universe's first second that has remained hidden all this time. There's even the mind-bending concept that dark matter could be a signature of extraspatial dimensions predicted by string theory, with gravity leaking into our world from these other realms. Each candidate points toward a different, profound extension of our understanding of physics. The continued non-detection of WIMP is not a failure but a guide, pushing us to think more creatively and to build even more clever experiments to listen for the faint, telltale signs of the invisible majority. While the theoretical possibilities are fascinating, the real drama unfolds in the colossal, multi-pronged experimental campaign to capture definitive proof. This global effort is a testament to human ingenuity, pushing the boundaries of technology in a quest to sense the seemingly insensible. The search is broadly divided into three distinct but complementary strategies: direct detection, particle collider production, and indirect observation of its cosmic aftermath. The most direct approach is to build a trap. This is the goal of experiments like LUX, Xenon, and their successors, which are located deep underground in abandoned mines or beneath mountains. Why underground? To shield the exquisitely sensitive detectors from the constant barrage of cosmic rays and background radiation that showers the Earth's surface. These facilities are technological marvels of purity and precision. Imagine a giant vat, sometimes containing several tons of ultra-pure liquid xenon, cooled to incredibly low temperatures. The core idea is to wait with immense patience for the rare and elusive event where a dark matter particle, perhaps a WIMP, passes through the detector and ever so gently bumps into the nucleus of a xenon atom. This tiny collision would produce two faint signals, a quick flash of scintillation light and a minute charge of electricity. Arrays of powerful sensors called photomultiplier tubes line the detector, poised to capture these minuscule signatures. The challenge is almost unimaginable. The interactions are so feeble that they could be drowned out by the natural radioactivity from trace amounts of elements in the surrounding rock or even from the detector materials themselves. That's why the hunt for dark matter is also a hunt for ultimate cleanliness and silence, requiring years of painstaking work to eliminate every possible source of interference. So far, these detectors have grown exponentially more sensitive, yet the dark matter particles have remained stubbornly elusive, a silence that is, in itself, a profound piece of data, gradually ruling out vast swaths of potential particle properties and masses. Simultaneously, physicists are trying a different tactic. Instead of waiting for dark matter to come to us, they are attempting to create it. This is the mission at the world's most powerful particle accelerator, the Large Hadron Collider at CERN. By smashing protons together at velocities approaching the speed of light, the LHC recreates the incredibly energetic conditions that existed a fraction of a second after the Big Bang. The hope is that this concentrated release of energy could momentarily conjure particles of dark matter out of the vacuum. Since these particles would not interact with the detector, they wouldn't be seen directly. Instead, their presence would be inferred by a telltale sign of missing energy and momentum. Picture one of those high-energy collisions. Scientists can meticulously account for all the energy and direction of the particles that are produced. If a significant amount of energy seems to simply vanish, carried away by something that left no trace in the detector, it could be the signature of a dark matter particle fleeing the scene. The LHC experiments, like ATLAS and CMS, are essentially cosmic crime scenes, looking for the clues left behind by an invisible culprit. While the discovery of the Higgs boson was a monumental triumph, finding dark matter at a collider would be an even more revolutionary achievement, allowing us to study its properties in a controlled laboratory setting for the very first time. The third major strategy takes the search back out into the cosmos, looking for the indirect fingerprints of dark matter interactions. This approach relies on the possibility that dark matter particles might not be completely stable. In regions of the universe with extremely high densities of dark matter, such as the centers of galaxies or within the vast halos that surround them, two dark matter particles could occasionally collide and annihilate one another. When they do, the theory suggests they would transform into a shower of secondary particles we can detect, such as gamma rays, the most energetic form of light, or neutrinos. Sophisticated space telescopes like the Fermi Gamma Ray Space Telescope are constantly scanning the sky, searching for unexplained, concentrated sources of gamma rays that could be the death cry of dark matter annihilation. Similarly, neutrino observatories buried deep in the Antarctic ice, like IceCube, are on the lookout for high-energy neutrinos that could have originated from similar events. Another fascinating indirect method involves looking for the subtle effects of dark matter on the smallest cosmic structures. If dark matter is slightly warm, meaning its particles move at a significant fraction of the speed of light, it would have a homogenizing effect, preventing the formation of very small dwarf galaxies. By counting the number of small satellite galaxies around the Milky Way and comparing it to supercomputer simulations, astronomers can place constraints on the temperature and therefore the mass of the dark matter particle. This global network of experiments spanning the depths of the Earth, the frontiers of particle physics, and the vastness of space represents one of the most ambitious scientific endeavors in history, a unified effort to illuminate the dark heart of our universe. To understand how this invisible substance could sculpt the entire visible universe, we need to journey back to the very beginning, to a time before the first stars, before the first atoms, to a cosmos that was almost perfectly smooth. In the immediate aftermath of the Big Bang, the universe was an incredibly hot, dense, and uniform soup of particles and energy, but not perfectly uniform. Thanks to quantum fluctuations that occurred in the first infinitesimal fraction of a second, there were tiny, random variations in density, ripples in the fabric of spacetime itself. These minuscule imperfections, these seeds of future structure, were imprinted on the cosmos and then stretched to macroscopic scales during a period of hyper-expansion called inflation. For the universe to evolve from this near-featureless state into the complex web of galaxies and voids we see today, something had to provide the gravitational anchor to amplify those tiny ripples. That something was dark matter. Imagine the early universe as a calm, flat sea. The ordinary matter in this sea, protons, electrons, and photons of light, were locked in a violent, inseparable dance. The photons were so energetic that they constantly smacked into the electrically charged particles, creating a thick, opaque plasma. This intense radiation exerted immense pressure, preventing the gas from collapsing under its own gravity. Any small clump of matter that tried to form would have been instantly blasted apart by the radiation pressure. It was an environment utterly hostile to the formation of any lasting structure. But dark matter held the key. Because it does not interact with light or electromagnetic forces, it was completely immune to this raging hurricane of radiation. Those primordial density fluctuations were just as present in the dark matter as they were in the normal matter, but for dark matter there was nothing to stop it. It could immediately begin to respond to the pull of gravity, ever so slowly starting to coalesce around those slightly denser regions. This was the critical head start that allowed the entire cosmic architecture to form. While the ordinary matter was trapped in a turbulent, luminous fog, the dark matter was quietly and relentlessly collapsing, building an invisible scaffolding, a cosmic skeleton of filaments and halos. This process created a vast gravitational landscape of wells and hills across the expanding universe. Once the universe cooled enough for electrons and protons to combine into neutral atoms, an event known as recombination, the photons were finally set free and the universe became transparent. With the radiation pressure suddenly gone, the ordinary gas was at last able to fall into the gravitational pits that the dark matter had already spent hundreds of millions of years preparing. The gas streamed along the invisible filaments of the dark web, pooling at the intersections where it condensed, fragmented, and eventually ignited into the first stars and galaxies. Every galaxy we see, from the smallest dwarf to the largest elliptical, formed at the heart of a much larger and more massive halo of dark matter. The size and shape of a galaxy, and even its eventual fate, are all dictated by the properties of this unseen dark matter anchor that holds it all together. Without this invisible foundation providing the initial gravitational blueprint, the universe would have remained a dark, formless, and perpetual expanse of diffused gas. The magnificent cosmic web, with its brilliant nodes of light connected by filaments of galaxies, is a direct map of the underlying dark matter distribution, a ghostly template upon which all of visible reality is painted. For centuries, the central question in cosmology was not if the universe was expanding, but how this expansion was changing over time. Since Edwin Hubble's groundbreaking work in the 1920s, we've known that space itself is stretching, carrying galaxies away from each other like raisins in a rising loaf of bread. The universal assumption, based on the fundamental force of gravity, was that this expansion must be slowing down. Every galaxy exerts a gravitational pull on every other galaxy. It seemed only logical that this mutual attraction would act as a cosmic brake, gradually putting a drag on the universe's initial outward momentum from the Big Bang. The ultimate fate of the cosmos hinged on this rate of deceleration. Would the pull of gravity be strong enough to eventually halt the expansion and pull everything back together in a fiery, big crunch? Or would the expansion just continue to slow for eternity, forever approaching a standstill but never quite reversing? This was the grand cosmological debate, and in the late 1990s, two rival teams of astronomers set out to settle it by measuring the deceleration rate with unprecedented precision. Their tool of choice was one of the universe's most reliable distance markers, a specific type of stellar explosion known as a Type 1 supernova. A Type 1 supernova is a cosmic bomb of incredible consistency. It occurs in a binary star system where a dense white dwarf star steals material from its companion. Once the white dwarf accretes enough mass, reaching a very specific threshold known as the Chandrasekhar limit, it triggers a runaway thermonuclear explosion that is, for a brief moment, brighter than an entire galaxy. Because the trigger mass is always the same, the intrinsic brightness or luminosity of these explosions is nearly identical. This makes them what astronomers call standard candles. If you know how bright something truly is, and you measure how dim it appears from Earth, you can calculate its distance with remarkable accuracy. Furthermore, by analyzing the light from the supernova, scientists can determine its redshift, a measure of how much the expansion of the universe has stretched its light waves, which tells us how much the universe has expanded since the explosion occurred. By comparing the distance to these supernovae with their redshifts, the teams, known as the Supernova Cosmology Project and the High Z Supernova Search Team, were meticulously mapping the expansion history of the universe. They were looking deep into the past, observing supernova billions of light years away, which meant they were seeing the universe as it was billions of years ago. Their goal was to see how much the expansion had slowed over cosmic time. The results, announced almost simultaneously in 1998, were not just surprising, they were utterly paradigm-shattering. Both teams found that the distant, ancient supernova were brighter, and therefore closer than their redshifts indicated they should have been if the universe had been expanding at its current rate. This counterintuitive data had a staggering implication. For these supernovae to be so close, it meant that in the past, the universe was actually expanding more slowly than it is today. The expansion wasn't slowing down at all, it was speeding up. The universe was not applying the brakes, it was stomping on the accelerator. This was the equivalent of tossing a ball into the air and instead of watching it fall back down, seeing it shoot away from the Earth faster and faster into the sky. It defied all conventional understanding of gravity and energy. The teams had to check and recheck their data for errors, for some overlooked source of dust dimming the more recent explosions, for any possible systematic flaw. But the result held. The discovery was so shocking that the leaders of the two teams, Saul Perlmutter, Brian Schmidt, and Adam Rees, were awarded the Nobel Prize in Physics in 2011 for what remains one of the most profound and unexpected discoveries in the history of science. This acceleration pointed to the existence of a mysterious, repulsive force that permeates all of space, working in opposition to gravity. The most favored explanation for this force harkens back to an old idea of Einstein's, a cosmological constant. He had originally introduced this mathematical fudge factor into his equations of general relativity to force a static, unchanging universe, which was the prevailing belief at the time. When Hubble discovered the expansion, Einstein famously called it his greatest blunder, but now it seemed the concept might have been prescient after all. This modern cosmological constant is what we now call dark energy. It is not a force in the traditional sense, but rather a property of empty space itself. The vacuum of space, according to quantum physics, is not truly empty. It is seething with virtual particles popping in and out of existence. This quantum foam is theorized to possess a fundamental energy density, and this energy has a repulsive gravitational effect. As the universe expands, more space is created, which means more of this repulsive dark energy comes into existence, causing the expansion to accelerate even further. It is a self-reinforcing, positive feedback loop that is destined to shape the ultimate fate of the cosmos in a cold, dark, and ever-accelerating isolation. The discovery that dark energy dominates the universe's energy budget, accounting for roughly 68% of everything that exists, completed a startling new cosmic census. Less than 5% is the ordinary matter we know. 27% is the invisible gravitational glue of dark matter, and the overwhelming majority is the enigmatic, repulsive force of dark energy. Dictating the future of everything, so we have two cosmic mysteries, both hidden, both dominant, yet with effects that are polar opposites. Dark matter acts as the universe's ultimate glue, pulling structures together through its immense gravitational influence. But dark energy is something else entirely. It is the universe's mysterious accelerator, a force that is not pulling things together but relentlessly pushing them apart on the grandest of scales. While dark matter sculpts the cosmic web, dark energy is determining the ultimate fate of that web, stretching the very fabric of space-time itself. The nature of this force is so counterintuitive it challenges our fundamental understanding of physics. We are accustomed to gravity being an attractive force. The Earth pulls on you, the Sun pulls on the planets, and galaxies pull on each other. This attractive pull is what dark matter provides in abundance. Dark energy, however, exhibits a repulsive form of gravity. It creates a kind of negative pressure or antigravity that causes the expansion of the universe to speed up. Think of it like this: if you throw a ball into the air, gravity slows it down and brings it back. Dark energy would be like throwing that same ball and watching it not only continue upward but fly away from you faster and faster into the sky forever. This isn't a force acting through space like magnetism. It is a property of space. It is as if the empty vacuum itself contains a latent energy that causes it to repel itself. The leading theoretical explanation for this bizarre behavior is Einstein's cosmological constant, represented by the Greek letter lambda in his equations of general relativity. He originally introduced this constant as a mathematical fix to achieve a static universe, which was the prevailing model of his day. When Edwin Hubble later discovered the universe was actually expanding, Einstein reportedly called the cosmological constant his greatest blunder. The irony is profound, for it now appears he may have been right for the wrong reason. In modern cosmology, the cosmological constant is interpreted as the energy density of the vacuum of space itself. Quantum physics tells us that what we perceive as a vacuum is not truly empty. It is a seething, bubbling foam of virtual particles constantly flickering in and out of existence. This quantum activity is thought to endow every cubic centimeter of space with a tiny, fundamental energy. On the scale of a coffee cup, this energy is negligible, completely undetectable. But across the vast, nearly infinite expanse of the universe, this tiny energy per volume adds up to an overwhelming, dominant force. And because this energy is a property of space itself, as the universe expands and more space comes into existence, more of this repulsive dark energy appears, causing the expansion to accelerate at an ever-increasing rate. It is a self-perpetuating cycle with profound and chilling implications for the distant future of our cosmos. And so we come to one of the most fascinating twists in the entire history of science, a story of a rejected idea making a triumphant and utterly unexpected return. The concept we now use to explain the accelerating universe, the cosmological constant, was first conceived by none other than Albert Einstein himself. In 1917, he was working on his revolutionary theory of general relativity, which describes gravity as the warping of spacetime by mass and energy. When he applied his magnificent equations to the universe as a whole, he encountered a problem. The prevailing scientific wisdom of the era held that the universe was static, eternal, and unchanging, a fixed cosmic stage. But his equations insisted that such a universe was impossible. The gravitational attraction of all the matter would cause it to inevitably collapse in on itself. To force his theory to align with the supposed static model, Einstein introduced a fudge factor, a term represented by the Greek letter lambda. This cosmological constant represented a repulsive force, a kind of anti-gravity that would perfectly balance the attractive pull of matter, creating a delicate equilibrium and allowing for a static, stable universe. Just over a decade later, the astronomer Edwin Hubble, using the most powerful telescope of his time at Mount Wilson Observatory, made an observation that shattered the static universe model. By carefully measuring the redshifts of distant galaxies, he discovered that they were all moving away from us, and crucially, that the farther away a galaxy was, the faster it was receding. The universe was not static at all, it was expanding. Einstein immediately realized that his cosmological constant was no longer necessary. The expansion naturally solved the problem of gravitational collapse. He famously called the introduction of the cosmological constant his greatest blunder, and he discarded it from his equations. For decades, the term was largely ignored, a curious footnote in the history of physics, a testament to even the greatest minds being products of their time. The universe, however, had a stunning surprise in store. The discovery of the accelerating expansion in the late 1990s turned this historical footnote into a headline. Those distant supernovae were telling us that not only was the universe expanding, but something was overpowering gravity and making it expand faster. Theorists scrambled for an explanation, and their eyes fell back upon that discarded idea gathering dust on the shelf. What if Einstein's blunder wasn't a blunder at all, but a moment of prescient genius? What if the cosmological constant was real, but its effect wasn't to create a static universe, but to govern the dynamics of an expanding one? This time, the repulsive force wouldn't need to perfectly balance matter. In an expanding universe with increasingly dilute matter, even a very small repulsive force would eventually become dominant. And that is precisely what the supernova data showed. That dark energy began to overtake the gravitational pull of matter about 5 billion years ago, and it has been steering the cosmic expansion ever since. The modern interpretation of the cosmological constant is deeply tied to the strange world of quantum mechanics. We now think of it as representing the energy intrinsic to the vacuum of space itself. According to quantum theory, what we perceive as empty space is not empty at all. It is a seething, bubbling foam teeming with virtual particles that constantly pop in and out of existence, borrowing energy from the vacuum for fleeting moments before annihilating each other. This chaotic quantum activity is believed to endow every tiny volume of space with a fundamental energy density. This vacuum energy would have a repulsive gravitational effect, exactly like Einstein's cosmological constant. The profound irony is that the greatest theoretical physicist of the 20th century introduced a concept to describe a universe that didn't exist, only for that same concept to be resurrected decades later to explain a universe far more strange and magnificent than anyone had ever imagined. His so-called greatest blunder may yet be remembered as one of his most insightful leaps. Confirming the reality of the accelerating universe required more than a single, albeit brilliant, method. The initial discovery using Type I, a supernova, was so revolutionary that astronomers knew they needed independent lines of evidence to corroborate it. They needed to measure the expansion history of the universe using completely different cosmic rulers and see if they all told the same astonishing story. This multi-pronged approach, a cornerstone of modern cosmology, relies on a toolkit of powerful observational techniques that peer into different epochs of cosmic history. The first and most direct method remains the use of Type I, a supernova. These stellar explosions continue to be vital standard candles, but the quest for precision has driven the development of massive automated sky surveys. Projects like the Dark Energy Survey and the upcoming Vera-C, Rubin Observatory's legacy survey of space and time, are designed to discover and measure not dozens, but thousands upon thousands of these cosmic beacons. By building a vast catalog of supernova across a wide range of distances, and therefore look-back times, scientists can construct an incredibly detailed movie of the universe's expansion. They can pinpoint the moment, roughly 5 billion years ago, when the gravitational tug-of-war between matter and dark energy tipped in favor of dark energy, and the expansion began to accelerate. This method effectively maps the universe's relatively recent history, providing a direct view of the acceleration itself. To cross-check this finding and probe even deeper into the past, astronomers turn to a fossil imprint from the adolescent universe, baryon acoustic oscillations, or BAO. This concept stems from the very early cosmos, when it was a seething plasma of light and matter. In this hot soup, gravity tried to pull matter into clumps, but the immense pressure from photons created powerful spherical sound waves that rippled outward, much like the circular waves from a stone dropped in a pond. These waves traveled for hundreds of thousands of years until the universe cooled enough for atoms to form, causing the photons to decouple and fly free. At that moment, the waves were frozen in place, etched into the fabric of the universe. The distance these waves traveled, about 500 million light-years across, became a permanent standard ruler. Today, by using enormous galaxy redshift surveys like the Sloan Digital Sky Survey, scientists can measure the apparent size of this frozen ring pattern in the distribution of galaxies. Because we know its true physical size from the physics of the early universe, we can use it as a calibration stick. By measuring how the apparent size of this ruler changes at different cosmic epochs, we can precisely track how the scale of the universe has expanded over billions of years. The BAO measurements provide a powerful and robust confirmation of the expansion history, completely independent of supernova, and they align perfectly with the accelerating universe model. The most profound validation, however, comes from looking back to the very beginning, to the afterglow of the Big Bang itself, the cosmic microwave background, or CMB. This faint microwave radiation is the oldest light we can see, a snapshot of the universe when it was just 380,000 years old. While it appears as a nearly uniform glow, sensitive space-based telescopes like the Planck satellite have mapped its tiny, millionth of a degree temperature fluctuations with exquisite detail. These fluctuations are not random. They form a precise pattern that encodes fundamental parameters of the cosmos. The sizes of the hot and cold spots in this pattern are exquisitely sensitive to the geometry and content of the universe. The observations show that the universe is geometrically flat, which, according to general relativity, means its total energy density must be exactly the critical density. When scientists add up the known densities of ordinary matter and dark matter, they only account for about 32% of what is needed. The remaining 68% required to make the geometry flat is the exact same amount of dark energy needed to explain the supernova observations. The CMB doesn't directly show the acceleration that began billions of years later, but it provides the initial conditions and the total budget. It tells us how much dark energy must have been present, lying dormant, waiting for the universe to expand enough for its repulsive effect to take over. The fact that these three completely independent methods, supernova, baryon acoustic oscillations, and the cosmic microwave background, all converge on the same cosmic recipe, with the same bizarre ingredient dominating our universe, is what gives scientists such tremendous confidence that dark energy is real. It is a triumph of cross-correlation where the universe's past, present, and future all tell a consistent, if mysterious, story. Yet with dark energy's reality so well established, the truly pressing question for physicists is no longer if it exists but what it truly is. To move beyond the label and start understanding its fundamental nature, scientists need a way to quantify its behavior, to measure its properties with precision. This is where we introduce a crucial concept in cosmology, the equation of state. In simple terms, an equation of state describes the relationship between the pressure and energy density of a substance. It's a way to classify how a particular component of the universe pushes or pulls as space expands. For dark energy, this relationship is defined by a single, deceptively simple parameter, denoted by the letter W. Think of W as dark energy's personality profile, a number that tells us how it will behave over time. The value of W determines whether the repulsive force of dark energy remains constant, grows stronger, or perhaps even weakens as the universe evolves. The leading candidate, Einstein's cosmological constant, predicts a very specific value, W equals -1. This value implies that the energy density of dark energy remains perfectly constant forever. As the universe expands and new space is created, the density of this vacuum energy does not dilute. It stays the same, meaning its repulsive influence grows ever stronger as more of it comes into being. However, the cosmological constant is just one theoretical possibility. Many physicists explore other, more dynamic models under the umbrella of quintessence. This concept imagines dark energy not as a static property of space, but as a dynamic energy field that evolves over time, similar to the inflationary field thought to have powered the Big Bang's initial burst of expansion. A quintessence field could have a value of W that is not exactly -1, and it could potentially vary over the history of the universe. If W is greater than -1, it would mean the strength of dark energy weakens slightly over time. If it were less than -1, a truly bizarre scenario often called phantom dark energy, it would mean the force grows stronger over time, not just because more space is being created, but because the energy density of the field itself is increasing. This phantom energy leads to a truly apocalyptic cosmic fate known as the Big Rip, where the repulsive force eventually becomes so powerful that it tears apart galaxies, solar systems, planets, and even atoms themselves in the distant future. This is why measuring the value of W with extreme precision is one of the most important goals in modern cosmology. It's the key that could unlock the true identity of dark energy. Astronomers use all their tools, supernova, baryon acoustic oscillations, and the cosmic microwave background, in a combined effort to constrain this number. The latest data from missions like the Planck satellite strongly favor a value very close to -1, consistent with the cosmological constant. The constraints are tightening, but the door is not yet closed on more exotic possibilities. The incredible precision of upcoming projects like the Euclid Space Telescope and the Vera C. Rubin Observatory will measure W with an error bar so small that it could finally rule out entire classes of theories. They are performing a deep cosmic autopsy, determining the exact parameters of the force that controls our ultimate destiny. The story of dark energy is far from over. We are currently in the process of writing its most crucial chapter, one precise measurement at a time. Given the monumental implications of dark energy, it's only natural that physicists have explored every possible avenue to explain the cosmic acceleration, including questioning the very foundation of our understanding of gravity. While the standard model of cosmology invokes dark energy as a mysterious component of the universe, a bold and intellectually daring alternative suggests that perhaps we don't need it at all. Maybe our theory of gravity, Einstein's magnificent general relativity, which has passed every test thrown at it for a century, might require modification on the largest conceivable scales. This line of inquiry asks a profound question. Are we inventing a mysterious, invisible energy to fill a gap, or is the gap actually in our theory itself? The most prominent of these alternative theories are often grouped under the term modified gravity, and their most famous progenitor is a hypothesis known as modified Newtonian dynamics, or MND. Proposed by physicist Mordechai Milgrom in the early 1980s, MND was actually designed to solve the dark matter problem, not dark energy. Milgrom noticed that in the outskirts of galaxies, where gravitational acceleration becomes incredibly weak, the observed rotation curves could be explained not by invisible matter, but by a simple modification to Newton's second law. His idea was that gravity might not behave as a pure inverse square law at these extremely low accelerations. Instead, it would become stronger. This single adjustment could beautifully explain the flat rotation curves of galaxies without invoking any unseen dark matter. For its intended purpose, MND was remarkably successful at predicting the motions within individual galaxies. When the accelerating universe was discovered, some theorists attempted to build upon this concept, creating relativistic versions of MND and other modified gravity theories that could also account for the cosmic acceleration. These theories are intricate and mathematically complex, but their core premise is to tweak the equations of general relativity so that the geometry of spacetime itself produces an accelerating expansion without needing any additional exotic energy component. It's an elegant idea in principle. Instead of adding a new, unexplained substance to the universe's inventory, we simply refine our description of how spacetime and gravity work. These theories aim for a more economical explanation, adhering to the philosophical principle known as Occam's razor, which favors simpler solutions with fewer assumptions. However, the challenge for any modified gravity theory is that it must do more than just explain one observation. It must explain all of them simultaneously, and it must do so as well as or better than the standard model. This is where these alternatives face their greatest difficulties. The bullet cluster, which provided such stunning evidence for dark matter, is a particularly devastating obstacle for theories like MND that try to eliminate dark matter. Remember, the gravitational lensing map showed that the majority of the mass was located with the galaxies, not the gas. A modified gravity theory that attributes galaxy rotation to a change in physics rather than unseen mass would still predict that the gravity should be strongest where the visible matter is most concentrated, which is in the gas clouds. The fact that the gravity is clearly divorced from the visible matter is a direct contradiction that MND alone cannot easily overcome. Furthermore, the standard cosmological model provides a single, unified framework that elegantly explains a breathtakingly diverse set of data. The precise features of the cosmic microwave background, the large-scale structure of the galaxy distribution revealed by baryon acoustic oscillations, the ages of the oldest stars, and the observed abundance of light elements from the Big Bang. Getting a modified gravity theory to correctly reproduce all these independent pillars of modern cosmology has proven incredibly difficult. Often, these theories can tweak their parameters to fit one set of data, but then fail to match another. The Standard Model, with dark energy and dark matter for all its mysteries, achieves this consistency with a remarkably small number of parameters. The convergence of evidence from supernova, the CMB, and BRO paints a picture that is challenging for any alternative theory to replicate in its entirety. This doesn't mean the effort is wasted. On the contrary, rigorously testing and challenging our foundational theories is how science progresses. These alternative ideas serve as crucial stress tests for the Standard Model, forcing cosmologists to double-check their work and ensuring that the case for dark energy is as rock-solid as it appears to be. For now, the weight of evidence remains overwhelmingly in favor of the dark energy paradigm, but the search for an even more complete theory of gravity continues. To truly appreciate the power of this cosmic snapshot, we must first understand what it is we're looking at. The CMB is the oldest light in the universe, a faint afterglow that fills every corner of the cosmos. Its story begins roughly 380,000 years after the Big Bang. Before this time, the universe was an opaque, seething plasma, far too hot and dense for atoms to form. Protons and electrons were constantly battered by powerful photons of light, trapped in a relentless, scatter-filled dance. But as the universe expanded, it cooled. Eventually, it reached a temperature cool enough for protons and electrons to finally combine and form neutral hydrogen atoms. In an instant, the fog cleared. The photons, which had been constantly bouncing around, were suddenly set free, able to travel across the universe in straight lines for the first time. We detect that first burst of liberated light today, stretched by 13.8 billion years of cosmic expansion from visible light into microwaves. It is a baby picture of the cosmos, a fossilized imprint of the universe in its infancy. This background radiation is incredibly uniform, a near-perfect blackbody with a temperature of just 2.7 degrees above absolute zero. But perfection is not what makes it interesting. What makes it the most important cosmological dataset ever collected are the tiny, exquisite imperfections, the anisotropies. When satellites like NASA COBE, WMAP, and the European Space Agency's Planck mapped the sky, they didn't find a perfectly smooth glow. They found minuscule fluctuations in temperature, variations on the order of 1/100,000th of a degree. These tiny hot and cold spots are not random noise. They are the seeds of all future structure in the universe, the gravitational blueprint for everything that would eventually form. They represent the primordial density fluctuations, the slightly denser regions that dark matter had already begun to clump around, and they hold encoded within them the precise recipe of the entire cosmos. Decoding this pattern is where the true magic happens. Scientists represent these temperature variations as a power spectrum, a graph that shows how much fluctuation exists at different angular scales on the sky. The precise shape of this spectrum is exquisitely sensitive to the fundamental parameters of the universe. It acts like a cosmic balancing scale. The locations and heights of the peaks in this spectrum tell a detailed story. The first peak, for instance, is related to the overall curvature of the universe. Its measured position confirms with incredible precision that the universe is geometrically flat. According to Einstein's theory of general relativity, this flatness means the total density of the universe must be exactly the critical density required to balance the expansion. When astronomers add up all the ordinary matter and all the dark matter they can infer, they only reach about 32% of that critical density. The remaining 68% must be something else with a repulsive gravitational effect to make the math work. This is the first and most fundamental evidence for dark energy from the CMB, proving its existence and quantifying its abundance long before the supernova observations were made. But the CMB's testimony doesn't stop there. The ratios of the heights of the second and third peaks are incredibly sensitive to the amount of ordinary matter versus dark matter. The gravity from normal matter, which interacts with radiation, suppresses certain acoustic oscillations. Dark matter, which is immune to radiation pressure, enhances others. By analyzing these subtle differences in the peaks, cosmologists can calculate the universe's matter composition with stunning accuracy. The Planck satellite data tells us that dark matter outweighs normal matter by a factor of about 5 to 1, and that together they make up about 32% of the cosmic energy budget. This independent measurement perfectly aligns with the observations from galaxy rotation curves and galactic clusters, creating a powerful consensus. The cold spots you see in a CMB map are not just empty voids. They are regions where dark matter had already begun to gather, its extra gravitational pull subtly affecting the light that passed through it. This ancient light doesn't just suggest the existence of dark matter and dark energy. It provides a precise, all-sky invoice of their exact amounts, a foundational document for our understanding of reality. While the cosmic microwave background gives us a pristine baby picture of the universe, it only shows us a flat, two-dimensional projection. To understand how the cosmos grew up, to trace the evolution of its structure from those initial seeds to the magnificent panorama we see today, we need a three-dimensional map. This is the monumental goal of massive galaxy surveys, which are essentially creating the most ambitious atlas of the universe ever conceived. These projects don't just catalog stars, they chart the positions and distances of millions, and soon billions, of galaxies across billions of light years, allowing us to reconstruct the largest structures in existence and watch how they've changed over cosmic time. The process begins with a monumental data collection effort. Powerful telescopes like the Sloan Foundation telescope used in the Sloan Digital Sky Survey perform wide-field imaging of huge swaths of the night sky. They capture the light from countless galaxies, but a two-dimensional image isn't enough. To build a true 3D map, we need to know how far away each galaxy is. This is where the phenomenon of redshift becomes our most vital tool. As the universe expands, it stretches the wavelength of light traveling through it. The farther a galaxy is from us, the longer its light has been traveling, and the more its light is shifted toward the red end of the spectrum. By carefully measuring this redshift from a galaxy's spectrum, astronomers can calculate its distance with remarkable accuracy. It's like adding a depth coordinate to every single point of light in the sky. Over years of painstaking observation, these surveys have painstakingly plotted the 3D positions of galaxies, revealing not a random scatter, but an intricate web-like architecture on the grandest possible scale. What emerges from this data is the cosmic web, a vast, frothy network of galaxies. This web is composed of dense clusters where thousands of galaxies swarm together, connected by long, thin filaments of galaxies and separated by enormous, empty voids that can be hundreds of millions of light years across. This structure isn't random. It is the direct descendant of the tiny fluctuations seen in the CMB, grown up and amplified by gravity over billions of years. And the primary architect of this web is dark matter. Those maps show the visible galaxies, but they are merely tracing the underlying gravitational landscape. The galaxies are like lights on an invisible Christmas tree. They show you the shape of the tree, but the tree itself is the dark matter halo. The distribution of galaxies we see is a near-perfect tracer of the distribution of the unseen dark matter that governs their motion. By studying the statistics of this web, the sizes of the voids, the thickness of the filaments, the number of massive clusters, scientists can precisely measure the total amount of matter in the universe and confirm the 5-to-1 ratio of dark to normal matter. But these maps do more than just confirm the past. They also reveal the present and future influence of dark energy. Remember, dark energy's repulsive effect began to dominate the universe's expansion about 5 billion years ago. This wasn't just a shift in expansion rate, it was a fundamental change in the rules of cosmic structure formation. Gravity is a force that works best over time. It needs time to pull matter together. Dark energy, acting as a sort of cosmic pressure, acts to oppose this clustering. When dark energy took over, it effectively put a brake on the formation of new large-scale structures. The cosmic web that had been forming for 9 billion years was essentially frozen in place, and its further growth was dramatically slowed. By comparing the web mapped by distant galaxies, which shows us the universe as it was billions of years ago, to the web formed by closer, more recent galaxies, astronomers can directly measure this suppression of growth. They can see how the rate at which clusters and filaments assembled slowed down when dark energy began to accelerate the expansion. The large-scale structure of the universe, therefore, is not a static monument. It is a dynamic record, its very evolution encoding the story of the epic struggle between the gravitational pull of dark matter trying to build and the repulsive push of dark energy trying to tear it all apart. So where does this accelerating expansion leave us in the grand scheme of things? The ultimate fate of the entire cosmos now hinges entirely on the precise nature of this mysterious dark energy. Its equation of state, that crucial parameter W, acts as a switch that points the universe toward one of several profoundly different endings, each more dramatic than the last. For a long time, cosmologists debated between two classic scenarios, but the discovery of dark energy introduced a third, even more extreme possibility that has reshaped our view of the distant future. The first and currently most favored scenario is known as the Big Freeze or heat death. This future is predicated on dark energy behaving exactly like Einstein's cosmological constant, with W firmly equal to -1. In this model, the acceleration continues at its current pace, relentlessly and forever. As billions of years turn into trillions and trillions into incomprehensible eons, the expansion keeps speeding up. Galaxies outside our local group will first fade from view as their light is redshifted into oblivion. Then they will be pushed beyond our cosmic horizon, disappearing from the observable universe entirely. Within our own galaxy, star formation will eventually cease as all the interstellar gas is used up or expelled. Existing stars will burn out one by one, leaving behind a cold, dark graveyard of black holes, neutron stars, and white dwarfs. Even these remnants are not eternal. Over timescales so vast they dwarf the current age of the universe, black holes will slowly evaporate via Hawking radiation, and protons themselves may decay. The final state would be a universe that is utterly dark, incredibly vast, almost perfectly empty, and just a fraction of a degree above absolute zero, a lonely, cold, and silent end. The second possibility is a return to an older idea, the Big Crunch. This scenario requires that dark energy is not a constant force but something that weakens over time, a form of quintessence where W is greater than -1. If this repulsive force were to diminish and eventually reverse, gravity could stage a comeback. After tens of billions of years of expansion, the universe would gradually slow, halt, and then begin contracting. Galaxies would start moving toward each other, the cosmic microwave background would blue shift and heat up, and the sky would grow hotter and brighter. The end would be the mirror image of the Big Bang, a rapid collapse of all matter and energy back into a singularity of infinite density and temperature. For a time, this was a popular theory as it offered a kind of cyclical universe, potentially giving rise to a new Big Bang and another cosmos in an endless cycle. However, the overwhelming evidence for accelerating expansion and a cosmological constant has made the Big Crunch seem far less likely, a relic of a pre-1998 understanding of the cosmos. The third and most violent option is the Big Rip. This is the destiny if dark energy is more terrifying than a cosmological constant, if it takes the form of phantom energy with a value of W less than -1. In this case, the repulsive force doesn't just remain constant, it actually grows stronger over time. The acceleration wouldn't just continue, it would become exponentially more violent. First, the expansion would tear apart galactic clusters, then individual galaxies. As the force intensifies, it would overcome the gravity holding our own Milky Way together, sending stars hurtling apart into the void. Then, as the end drew near, the expansion force would exceed the gravitational bonds holding solar systems together, and later, the forces holding planets and stars together. In the final moments, the repulsive force would become stronger than the atomic forces binding molecules, then atoms, and finally the very nuclei of atoms themselves. The universe would end in a catastrophic, instantaneous shredding of all structure, from the largest galaxy to the smallest subatomic particle, ripped apart by the expansion of space itself. This is the most dramatic and definitive end possible, a true singularity of destruction. Which of these fates awaits us? The answer lies in that single number, W. Our current best measurements from Planck and other observatories point to a value incredibly close to -1, making the Big Freeze the overwhelming favorite. But the error bars have not yet closed completely on more exotic possibilities. The next generation of telescopes, like the Euclid Space Mission and the Vera C. Rubin Observatory, are designed to measure W with unprecedented precision, to finally tell us if our future is one of cold isolation, fiery collapse, or total annihilation. The story of our universe's end is not yet written. We are living in the era where we first get to read its opening chapters. Yet for all its explanatory power, the cosmological constant presents us with perhaps the most glaring and embarrassing problem in all of theoretical physics. A calculation so spectacularly wrong it has been called the worst prediction in the history of science. The issue is not with the concept itself, but with the numbers. When physicists use the well-established rules of quantum mechanics to calculate the theoretical energy density of the vacuum, the very energy we're calling the cosmological constant, they arrive at a number. This prediction is based on summing up all the fleeting quantum fluctuations, the virtual particles that pop in and out of existence in the vacuum of space. It is a messy calculation, but it gives a result. That result is staggering. The predicted value for the vacuum energy density is a number so immense it defies comprehension. It is approximately 120 orders of magnitude larger than the value we actually observe for dark energy. To grasp the sheer scale of this error, consider this. If the predicted value were correct, the repulsive force of this vacuum energy would have been so unimaginably powerful that it would have torn the universe apart in the first fraction of a second of its existence. Stars, planets, and galaxies could never have formed. The universe as we know it would be impossible. Clearly, our prediction is catastrophically incorrect. This yawning chasm between theory and observation is known as the cosmological constant problem. It is not a small discrepancy to be tweaked. It is a fundamental failure of our two most successful theories, quantum mechanics and general relativity, to agree on the most basic property of empty space. It suggests we are missing a profound piece of the puzzle, a cancellation mechanism or a new symmetry in nature that brings this enormous number down to the tiny, but non-zero, value we observe. Imagine calculating the weight of a single grain of sand and getting an answer equivalent to the mass of the entire observable universe. The error is so vast it implies our entire approach is fundamentally flawed. Physicists have proposed several ingenious, though still speculative, solutions to this monumental problem. One of the most prominent is the idea of supersymmetry, a theoretical framework that posits every known particle has a heavier superpartner. In a perfectly supersymmetric universe, the positive and negative contributions of these particles and their partners to the vacuum energy would cancel each other out exactly, resulting in a net energy of zero. This would solve the problem, but there's a catch. We do not see these superpartners in our current universe, meaning if supersymmetry is real, it must be a broken symmetry, and the cancellation would no longer be perfect. It could leave behind a small, residual energy that matches our observations of dark energy. However, experiments at the Large Hadron Collider have so far found no evidence for these superpartner particles, casting some doubt on this elegant solution. Another possibility, even more mind-bending, is the concept of the multiverse. In this scenario, our universe is just one of a vast, perhaps infinite, number of universes, each with its own unique set of physical constants and laws. In most of these universes, the cosmological constant is indeed enormous, rendering them sterile and lifeless. But by sheer chance, in a tiny, insignificant fraction of them, the value is small enough to allow galaxies and life to form. We, of course, find ourselves in one of those rare, habitable universes. This anthropic explanation is deeply controversial because it shifts the question from "why is the constant so small?" to "in which universe is the constant small enough for us to exist?" While it offers a potential answer, many physicists find it unsatisfying because it moves the goalposts from a fundamental physical explanation to a statistical coincidence. Whether through a yet-to-be-discovered symmetry, a revolutionary new theory of quantum gravity, or a multiverse landscape, the cosmological constant problem remains a stark reminder of how much we still have to learn about the true nature of reality at its most fundamental level. These enigmatic concepts have not only revolutionized astrophysics, but have also fired the imagination of storytellers, weaving their way from scientific journals into the very fabric of our popular culture. This journey into the mainstream often begins with a necessary simplification, a process that can both illuminate and occasionally distort. When a blockbuster film needs a plot device of cosmic proportions or a video game requires an awe-inspiring mystery, dark matter and dark energy provide a perfect, scientifically grounded foundation for the fantastic. Think of the mysterious substance in the Mass Effect video game series, where Element Zero or EZO is a material that can alter the mass of objects, allowing for faster-than-light travel. While not a perfect analog, it draws a direct line from the real-world mystery of dark matter's gravitational influence to a tangible, story-driving element. Similarly, the television series Stargate Universe featured an ancient spaceship, the Destiny, powered by tapping energy from the cosmic microwave background, a clever nod to the universe's fundamental energy fields that echoes the hunt for dark energy's origins. However, this translation from complex science to compelling narrative often leads to creative liberties that create lasting misconceptions. A common trope, particularly in action and superhero genres, is to portray dark matter as a volatile, glowing, and incredibly dangerous substance. We might see it stored in glowing containers, weaponized into energy blasts, or even as an infectious agent. In reality, its defining characteristic is its profound lack of interaction. It doesn't glow, explode, or infect because it barely notices that normal matter exists. It is the ultimate cosmic ghost, not a cosmic battery. These portrayals, while exciting, can unfortunately cement the idea that dark matter is just another form of exotic matter with bizarre physical properties, rather than a fundamental, invisible component of the universe's structure. Beyond these literal interpretations, dark energy and dark matter have become powerful metaphors. They serve as a cultural shorthand for the unknown, the unexplainable forces that shape our lives in ways we cannot fully perceive. A character might describe a hidden political influence as social dark matter, or a novelist might use the accelerating expansion of the universe as a poignant allegory for the emotional drift between two people. This metaphorical use demonstrates how deeply these ideas have permeated our collective consciousness. They have become a new language for discussing mystery itself. The very phrase dark in their names contributes to this aura of mystery, though in astronomy, dark simply means not visible, not necessarily sinister or evil. Yet that same terminology fuels narratives about ominous, unseen forces, playing into our innate fascination with what lies just beyond our perception. This cultural absorption is ultimately a testament to the profound allure of these cosmic mysteries. The fact that 95% of reality is composed of something we cannot see or directly touch is a concept that resonates on a deeply human level. It challenges our perception of what is real and solid, inviting both scientists and artists to explore the boundaries of the known. While a movie might get the physics delightfully wrong, it can still capture the sense of wonder and humility that comes from confronting the vast unknown. It sparks curiosity, prompting viewers to ask questions and seek out the real science behind the fiction. In this way, popular culture acts as a bridge, taking the esoteric concepts of cosmology and delivering them to a wide audience, igniting the spark of discovery in the next generation of scientists who might one day finally shed light on the darkness. Today's most ambitious telescopes are no longer just cameras pointed at the stars. They are highly specialized cosmic detectives, each designed to uncover a specific piece of the dark universe puzzle. They work in concert from the deep freeze of space to remote mountaintops on Earth, employing a breathtaking array of technologies to sense the invisible. This global observatory is our best hope for turning these cosmic mysteries into understood physics. Soaring 1,000,000 miles from Earth, the James Webb Space Telescope represents a monumental leap in our ability to peer into the cosmic dawn. While not specifically designed to detect dark matter particles, its profound contribution lies in mapping the universe's early structure. By observing the very first galaxies and quasars that formed, Webb allows us to test our theories of how dark matter's gravitational scaffolding guided the assembly of the universe. Seeing these infant structures helps us understand the initial conditions and properties of dark matter, providing crucial data to refine our models. It's like getting a clearer, high-resolution baby picture, allowing us to see the detailed blueprint from which everything grew. Back on Earth, perched high in the clear, dry air of the Chilean Andes, the Vera Sea, Rubin Observatory is preparing for a mission of unprecedented scale. Its cornerstone is the Legacy Survey of Space and Time, or LSST, a 10-year project that will photograph the entire southern sky every few nights. This will create the largest astronomical movie ever made, cataloging billions of galaxies and tracking how their positions change over time. The Rubin's immense power isn't in looking deeply at one spot, but in looking widely at everything repeatedly. This will allow scientists to measure the subtle distortions caused by weak gravitational lensing, the warping of light by dark matter, with incredible statistical precision, creating the most detailed map yet of the dark matter web across the universe. Meanwhile, the Euclid Space Telescope, a mission led by the European Space Agency, shares a similar lensing goal but from the pristine vantage point of space. Euclid is specifically engineered to achieve exquisitely sharp images over a huge area, minimizing the atmospheric blurring that affects ground-based telescopes. Its primary mission is to measure the shapes of over 1 billion galaxies, constructing a 3D dark matter map of the universe that spans 10 billion light-years. By combining this lensing map with measurements of how galaxies are clustered, Euclid will deliver a powerful, independent measurement of dark energy's equation of state, that crucial W parameter, helping to determine if it truly is a constant or something more dynamic. On a different front, the Dark Energy Spectroscopic Instrument, or DESI, is attacking the problem from yet another angle. Mounted on a telescope in Arizona, DESI isn't primarily looking at shapes. It's capturing light from tens of millions of galaxies and quasars to measure their spectra and obtain precise redshifts. This allows it to construct an enormous 3D map of the universe's large-scale structure. Its key goal is to measure baryon acoustic oscillations, those frozen sound waves from the early universe, as a standard ruler. By tracking how the apparent size of this ruler changes across different cosmic epochs, Dacey provides a direct and incredibly precise history of the universe's expansion, charting the accelerating influence of dark energy over the last 11 billion years. Beyond these massive galaxy surveys, the hunt for dark matter particles continues in extreme environments. The Fermi Gamma Ray Space Telescope scans the sky, searching for unexplained bursts of high-energy gamma rays that could be the signature of dark matter particles annihilating each other in dense regions like the center of our galaxy. And deep underground, in abandoned gold mines and beneath mountains, experiments like LZ and Xeno NNT continue their patient vigil, using tons of liquefied noble gases in their quest to record the infinitesimally rare vibration of a dark matter particle striking an atomic nucleus. This multi-pronged investigative effort, from the grandest cosmological surveys to the most sensitive underground detectors, forms a coordinated campaign to finally shed light on the dark universe. While our most powerful telescopes scan the skies and underground detectors listen for faint whispers, another equally vital search is happening in the realm of pure theory. The profound mysteries of dark matter and dark energy are not just observational challenges. They are screaming clues that our two most successful theories of physics, quantum mechanics, and general relativity are fundamentally incomplete. They work flawlessly in their own domains, the ultra-small and the ultra-large, but they refuse to speak the same language. Unifying them into a single, coherent framework, a theory of quantum gravity, is perhaps the holy grail of modern physics, and it is within these ambitious theoretical frontiers that we might finally find the ultimate answers to our dark universe. One of the most prominent and mathematically elegant candidates is string theory. At its heart, string theory proposes a radical departure from the idea of point-like particles. Instead, the fundamental building blocks of the universe are unimaginably tiny, vibrating loops of energy strings. Just as a single violin string can vibrate at different frequencies to produce distinct musical notes, these cosmic strings vibrate at different resonant frequencies, and each unique vibration manifests as a different fundamental particle, like an electron or a quark. The mathematics of string theory is beautiful and powerful, but it comes with a staggering requirement. For the equations to be consistent, the strings must vibrate in not just the 3 spatial dimensions we experience, but in 10 or more dimensions. The theory suggests that these extra dimensions are curled up or compactified at a scale so infinitesimally small that we cannot perceive them. This is where string theory potentially intersects with our cosmic mysteries. The specific way in which these extra dimensions are compactified determines the properties of the universe we observe, the laws of physics, the forces, and crucially, the particles that exist. It is within this landscape of possible configurations that physicists search for a version that naturally produces a stable dark matter candidate. One possibility is that the lightest supersymmetric particle, often called a neutralino, could be stable and could have exactly the right properties to be a WIMP. String theory provides a natural home for supersymmetry, making it a compelling, though still unproven, pathway to explaining dark matter. Furthermore, the energy associated with the vacuum in string theory, the cosmological constant, could be derived from the geometry of these compactified dimensions. The monumental challenge, known as the string landscape, is that there may be a virtually infinite number of ways to curl up these extra dimensions, leading to a multiverse of possible universes with different physical constants. Finding the one that matches our universe with its peculiarly small but non-zero dark energy is a task of mind-boggling complexity. Supersymmetry, or SUSY, is a cornerstone of many of these theoretical efforts even beyond string theory. It proposes a profound and elegant symmetry between the 2 fundamental classes of particles, fermions which make up matter and bosons which carry forces. For every known particle, SUSY predicts a heavier superpartner. The electron would have a selectron, the quark would have a squark, and the photon would have a photino. This symmetry is mathematically beautiful because it solves several nagging problems in particle physics at once. For dark matter, it offers a perfect candidate, the lightest supersymmetric particle, or LSB. If SUSY is true, the LSB would be stable, electrically neutral, and only interact weakly, making it a textbook WIMP. It would have been produced in abundance in the hot Big Bang and would persist today as dark matter. The catch is that for this to work, supersymmetry must be a broken symmetry in our current, cooler universe. If it were perfect, we would already see these superpartners everywhere. This means the particles must be heavy enough to have evaded detection so far. Experiments at the Large Hadron Collider have been actively hunting for signs of these superpartners, but as of yet, they remain elusive, pushing the possible mass range for these particles higher and higher. Beyond these established ideas, more radical concepts are emerging from the quest for quantum gravity. Some theories propose that dark matter might not be a particle at all, but a manifestation of the granular nature of space-time itself. Just as atoms are the fundamental units of matter, some models suggest that space-time may have a fundamental pixelation at the incredibly tiny Planck scale. The energy and dynamics associated with this quantum foam could potentially contribute to the phenomena we attribute to dark matter and dark energy. Another fascinating idea revolves around the holographic principle, which suggests that all the information contained in a volume of space can be described on its boundary, much like a hologram. This principle, born from black hole physics, could lead to a radically different understanding of gravity and vacuum energy, potentially explaining the cosmological constant problem by redefining how we calculate the energy content of the universe. These theoretical frontiers represent humanity's most ambitious intellectual effort to grasp the true nature of reality. They are not mere abstract speculations, they are rigorous mathematical frameworks that make testable predictions. The ongoing silence from particle colliders and direct detection experiments is itself valuable data, guiding theorists away from certain ideas and toward others. Whether the answer lies in the vibrational modes of tiny strings, the broken symmetry of supersymmetry, or a revolutionary new principle from quantum gravity, the pursuit is driven by the conviction that the universe is ultimately comprehensible. The darkness that dominates our cosmos is not a void of understanding, but a canvas upon which the next great theory of everything will be painted. This overwhelming dominance of the invisible universe isn't just a curious detail in an astronomy textbook. It represents a profound and humbling crisis at the very heart of physics. We have built two magnificent and incredibly successful pillars of understanding: the Standard Model of particle physics, which describes the quantum world of the very small with breathtaking precision, and Einstein's general relativity, which masterfully explains the force of gravity and the large-scale structure of the cosmos. The problem is that these two pillars are built on completely different foundations, and worse, they are both utterly silent on 95% of what actually makes up the universe. This isn't a small gap in our knowledge, it's a yawning chasm that suggests our most fundamental theories are, at best, incomplete, and at worst, merely a good approximation of a much deeper, stranger reality. Think of it like this: for centuries we have been meticulously studying the visible, tangible world, developing complex laws to explain how it operates. It would be as if we had perfected a complete science of ocean foam, with detailed equations predicting the exact size of bubbles and the patterns of spray, all while remaining completely oblivious to the existence of the vast, deep ocean of water beneath it that governs everything the foam does. Our Standard Model is a triumphant theory of the foam, the 5% of ordinary matter. It has predicted the existence of particles like the Higgs boson with stunning accuracy. But it has no candidate for dark matter that fits neatly into its framework, and it catastrophically miscalculates the energy of the vacuum, which we call dark energy, by a factor of 1 followed by 120 zeros. This isn't a small error, it's the biggest discrepancy between theory and observation in the entire history of science. General relativity, for its part, beautifully describes how mass and energy warp spacetime to create the force we experience as gravity. It perfectly predicts the orbit of Mercury, the bending of light around stars, and the existence of black holes. But it merely describes the effect of dark matter and dark energy. It doesn't explain their fundamental nature or origin. It tells us that the universe is expanding at an accelerating rate, but it doesn't tell us why. Einstein's equations can accommodate a cosmological constant, but they cannot derive its value from first principles. We are left with a description of the universe's behavior without an understanding of its engine. This is why the hunt for dark matter and dark energy is so much more than a niche astronomical pursuit. It is the forefront of a scientific revolution. Cracking this mystery will almost certainly require a paradigm shift as profound as those triggered by quantum mechanics or relativity itself. We are being forced to consider ideas that once belonged solely to the realm of philosophy and science fiction. Extra dimensions of space as proposed by string theory, a multiverse of countless universes with different physical laws, or even more radical concepts where space and time themselves are not fundamental but emerge from a deeper, more basic structure of reality. The answers will not come from simply tweaking our existing models. They demand a leap into the unknown, a willingness to rewrite the textbooks and embrace a new, more complete theory of everything that can finally unite the quantum world with the cosmic scale and illuminate the true nature of the dark universe that has until now remained hidden in plain sight. This grand challenge of unification pushes us to consider that the answers to the universe's largest mysteries might be hidden in the behavior of the very smallest things. To truly understand dark matter and dark energy, we cannot just look out at the cosmos. We must also look inward into the quantum realm and find a way to bridge a fundamental divide that has persisted for a century. The force that governs the vast cosmic architecture of galaxies and the expansion of the universe itself is gravity, described with magnificent accuracy by Einstein's general relativity. Yet the other three fundamental forces, electromagnetism and the strong and weak nuclear forces, are described by the completely separate and equally successful framework of quantum mechanics. This is the great schism in modern physics. We have two rule books for the universe, and they are written in different languages. General relativity is a classical theory, painting gravity as the smooth curvature of spacetime by mass and energy. It gives us black holes, gravitational waves, and the expanding cosmos. Quantum mechanics, on the other hand, reveals a subatomic world that is probabilistic, granular, and governed by discrete particles and fields. This quantum description works perfectly for the other forces, but all attempts to describe gravity in the same quantum terms have failed spectacularly. The equations break down, producing nonsensical infinities whenever we try to apply them to the incredibly dense, small-scale conditions where gravity becomes strong, such as the center of a black hole or the first moment of the Big Bang. This tells us that our current theories are incomplete. They are approximations that work well in their own domains but cannot handle the extremes where the domains overlap. This is precisely where dark matter and dark energy enter the stage, not just as puzzles to be solved, but as potential guides. They are cosmic phenomena that appear to be governed by gravity, yet their fundamental nature seems to lie in the quantum world. Dark matter, for instance, is almost certainly a new, fundamental particle that doesn't fit into the standard model of particle physics. Discovering it would be the first concrete evidence of physics beyond that established model, a direct message from the quantum realm about what we're missing. Its properties could provide crucial clues about how to build a theory of quantum gravity, perhaps pointing toward supersymmetry or other extensions of the standard model. Dark energy presents an even deeper conundrum. Its leading explanation, the cosmological constant, is fundamentally a quantum concept. It is the energy of the vacuum itself, generated by the frantic activity of virtual particles popping in and out of existence. The problem, as we discussed, is that our straightforward quantum calculation of this energy is catastrophically wrong, overshooting the observed value by a factor of 10 to the power of 120. This isn't just a small error, it is the clearest possible signal that we are missing a fundamental piece of physics. It suggests that a successful theory of quantum gravity must include a mechanism, perhaps a new symmetry or a revolutionary principle, that explains why the vacuum energy is so much smaller than it should be. In this way, dark energy is not a side issue. It is a central key that could unlock a deeper understanding of how the quantum vacuum and the curvature of spacetime are intrinsically linked. The quest to unify these scales is the driving force behind theories like string theory and loop quantum gravity. String theory, for example, proposes that the fundamental constituents of the universe are not point-like particles but tiny, vibrating strings. The different vibrations of these strings correspond to different particles, including potentially the graviton, the hypothetical quantum particle that would carry the gravitational force. The mathematics of string theory naturally requires more than the three spatial dimensions we see, suggesting that the properties of our universe, including the strength of gravity and the value of the cosmological constant, might be determined by how these extra dimensions are curled up and hidden from view. From this perspective, the values of dark matter and dark energy are not random. They are locked in by the geometry of the quantum landscape. Ultimately, dark matter and dark energy are the two most compelling pieces of observational evidence telling us that a deeper theory must exist. They are the cosmic phenomena that demand a marriage between the infinite and the infinitesimal, a theory that can seamlessly describe the gravitational dance of galaxies and the quantum jitter of the vacuum with a single, coherent set of equations. Solving these mysteries won't just tell us what the invisible 95% of the universe is. It will fundamentally rewrite our understanding of reality itself, finally giving us a complete picture of how the universe works from the smallest quantum fluctuation to the largest cosmic horizon. And so we are left with this breathtaking realization, a truth that fundamentally reshapes our place in the cosmos. For all our knowledge, for all our powerful telescopes and brilliant minds, we have been studying little more than the visible frosting on a vast, dark cake. The grand stage of the universe, with its swirling galaxies and brilliant stars, is merely a luminous decoration on a framework built from something we cannot see, governed by a force we do not understand. Dark matter and dark energy are not just minor curiosities. They are the dominant reality, the hidden architects and engine of everything that exists. This is the ultimate lesson in humility, revealing that the universe we perceive with our senses is but a tiny sliver of a much deeper, richer, and more mysterious whole. Yet, this profound ignorance is not a cause for despair, but for exhilaration. It represents the most exciting and expansive frontier in all of modern science. Every unanswered question is an invitation to explore, a puzzle waiting for its solution. The mystery of dark matter pushes us to dig deeper underground and build more powerful colliders, searching for ghostly particles that could redefine the fundamentals of matter. The enigma of dark energy challenges us to peer farther back in time and to question the very laws of physics, perhaps leading us to a revolutionary theory of quantum gravity that unites the cosmos. This is where the next great breakthroughs will happen, at the intersection of the cosmic and the quantum, in the space between what we know and what we have yet to imagine. The story of dark matter and dark energy is the story of science itself, a relentless collaborative journey into the unknown, driven by curiosity and the unwavering belief that the universe, no matter how strange, is ultimately knowable. It connects the painstaking observations of astronomers like Vera Rubin to the monumental equations of theorists like Einstein, and it now rests in the hands of a global community of scientists working to illuminate the darkness. So what do you think lies in that hidden 95%? Do you find the idea of a universe dominated by invisible forces thrilling or perhaps a little unsettling? Share your thoughts and your own theories in the comments below. I love hearing your perspectives on these mind-expanding topics. And if you want to join us as we continue to explore the farthest reaches of science and technology, be sure to subscribe and hit the bell so you don't miss our next deep dive into the future.